We present a system that can generate structured 3D printable models with spatially varying elastic properties, like this armadillo with soft and stiff regions, using only a single base material. We exploit the fact that the elastic behavior of an object is determined not only by the material that is used, but also by the small-scale structure embedded in the object. Our core contribution is a method that combines multiple structures to generate objects with a large range of elastic properties, printed with only a single material. Our method tackles two basic problems. First, we approach the question of how to efficiently generate a structure for a given elastic behavior. During pre-processing, we build a data-driven model that can generate such structures. We then look at the problem of how to combine multiple distinct structures inside a single object. This enables us to generate objects with spatially varying elastic properties. In the first step, we want to build a model that we can use to generate structures for a given set of elastic parameters, and we want this model to work for a large range of elastic parameters. We do this by collecting a set of structures with different properties, using them to generate new structures through interpolation. However, this interpolation might fail if the structures are not similar enough. We therefore build a family of structures in which individual structures are similar to each other. Using such a family for our model allows for smooth interpolation. With this, we are able to create a continuous space of structures. To create such a family of structures, we introduce an algorithm that iteratively searches for new structures that both have the desired elastic behavior and a shape similar to already computed structures. With this construction scheme, we can generate a family that spans a large range of properties. Such a family is not unique, and different families might cover a different range of properties. To increase the expressiveness of our method, we combine multiple families in our model. Once the pre-processing is done, the final model that we generate can be saved for later use and even shared with other people. Based on this model, we can then tackle the problem of how we generate a printable object consisting of different structures. To create a model based on the families of structures we created, we start from an input model with a desired distribution of elastic properties. We discretize this model into coarse cells, each of which will be filled by a single structure that has to be compatible with its neighbors. Since we use multiple families of structures, we generate a set of candidates for each cell that we want to fill. From these candidates, we choose the structures that are most compatible. Neighboring structures have to fit, meaning that they connect across tile boundaries, and they have to work together, meaning that forces are consistent across tile boundaries. After choosing a set of structures, we combine them to create a model that we can 3D print. We use our model to generate and print a number of examples. The virtual description of this bunny specifies one soft and one stiff ear, as well as spatially varying elastic properties in the rest of the body. Our method can directly translate this description into a printable model. This teddy model also exhibits spatially varying elasticity. Notice how one of the arms and one of the legs is softer than the other. This armadillo is designed to have soft regions around the arm and leg joints, the torso, and the neck, while the rest remain stiff. The result is an articulated character with movable arms and legs without any mechanical joints. We also used our algorithm to generate a soft robot. By designing this sheet with anisotropic elastic properties and rolling it into a tube, we create a finger that will bend in a specific direction when the air pressure is increased on the inside. 2 of these fingers can be used to create a gripper that can lift objects. Thank you for your attention.